you know, we might have some long-term potential. Yeah.
You bring your parents next time.
Yeah, we love to.
This is Michael Clyde. We like to call him Clyde. I'm Simone Sayed, and this is Scott Norman. And we help curate Space Salon. And we're really happy you guys can make it out.
And the curation manage, operate, curate. I like that. It's kind of like a garden. So three of us kind of were part of creating this thing called Space at Los Angeles. And Space at Los Angeles, for those of you who weren't there, there's like 4 of you. It's called an unconference. An unconference is a way to have a conference with a lot of really high-end, kind of like really talented people talking, but also allow everybody in the audience, ranging from other rocket scientists or journalists to people fresh out of college or fresh out of high school to interact with each other. And kind of like our point of the salon here is trying to get a little bit of that, in addition to a seminar. So, audience participation is encouraged, and and so whatever you really feel like saying, go ahead and say it. It's kind of more open forum, and you see by our seating arrangements and everything, we've designed it such that you feel more welcome as a participant member. But I'm going to go ahead and just tell you what we got special today. We got Doug Jones here. First time I met Doug Jones a couple years ago at this little rocket company called XCOR Aerospace out in the middle of Mojave. And back then, I was still working in movies. And I just come out there because, my friends said, oh, you should come check it out. This event, we're going to fire up a rocket engine. I go and I meet him, like, it fires off this little tiny rocket engine that makes this beautiful green flame. And, I was like, wow, it's really cool. I didn't even know this place existed until today. And so I started, showing up more and more often. And finally one day, I asked my buddy Mark, hey, Mark, can I come out to this rocket test? We're going to test the big rocket. So, only thing. And I go in there, and Doug's sitting there during the rocket test, sitting there on a keyboard, working an Excel file the whole time. And then halfway through the test, he just says, everybody shut up. And just listens very, very, very closely to the rocket. And he's just like a eureka moment and goes back down and gets back to typing. That's why he's kind of known as the rocket whisperer. He's the only guy I've ever met who diagnosed rocket problems by listening to them.
It helps that I'm half deaf.
Yeah.
It's the cause of your being half deaf.
That's a good question. Well, I ended up working for him, and now he's one of my many bosses. I'm very proud to present Doug Jones, the rocket whisperer, who's going to be talking about mostly not XCOR stuff. He's going to be talking about the future of space transportation, like what is beyond what we are doing now. Because we spend a lot of time in our office working on what's right now and tomorrow. But we also got to keep our eye open for the next generation, and specifically the next realistic generation. We're not going to be talking about workforce or I don't know. Are we going to talk about workforce?
No, we're talking about things that seem fantastic, but are actually physically doable with technology we know about.
So he's going to talk about that, and so I'm going to get out of his way.
Okay. So is this going to a PA system, or is it just for recording?
Just for recording.
Yeah, that's a good question.
Okay, so I guess I'll just have to turn my hearing aids off so I can project a little bit better. Trouble with doing too many rocket engine tests is that it does have certain side effects. And actually, most of my hearing loss is utterly unrelated to my work. But it actually does turn out that with the feedback reduced, I managed to project a little bit more. So first I'm going to talk a little bit about XCOR, who we are, where we started, and where we hope to be in a few years. And then it's where do you take up from after we've succeeded wildly beyond our greatest dreams. So this is one of our engines at XCOR. This was the largest one we built to date. It was the 5M15 engine that we built for NASA with some help from ATK, mostly running interference with NASA. And 7,500 pounds thrust, and it really is kind of fun to be sitting in the bunker just out of sight to the left of this photo, flip a switch and hear that roar coming from the outside. And in case you were wondering why we've got something venting while the engine is running, that's just oxygen that we were running a prime valve up to the main liquid oxygen valve to get nice cold locks to right there so that the start transient on the engine would go quicker. Because if you got warm oxygen in the line leading from the tank to the engine, it takes a while for it to get all the way up to full thrust because that oxygen is warm and low density. So that's just, in case you were wondering. And those are shock diamonds coming out of the engine. You can barely see that the engine is actually running because the stuff's burning so clean. And it's just a lot of fun to work on that project. And with any luck, next year we'll be running another engine with an even more transparent exhaust running on hydrogen. So next, please. We got started 12 years ago, excuse me. They're all blending together in my head at this point. We're up there in the desert in Mojave, the fashionable place for rocket companies, as I like to say. There's a lot of them on the airport, but we're one of only 2 that have actually flown people. We've built a lot of rocket engines. We've built 2 rocket airplanes. That's the X-Racer at the top, the Easy Rocket in the middle on the left, methane engine there on the right. Our first engine, right down there in the lower left, was a little 2P1. That was the small engine that Clive was talking about. And on the lower right there is a little interesting thing. That was our firewall test stand. It's where the power plant for the X-Racer rocket airplane was tested on that. And that test stand actually had a pilot's seat on it, so that the pilot, before he flew the plane for the first time, could sit down on the test stand and run that engine and get comfortable, get familiar with it, know what it sounds like before he's going to be flying the thing, so that he's got a little bit more training before he has to go up there and take control of this ridiculously overpowered airplane. So next. So there's the Easy Rocket, the X-Racer, and the 2 renderings on the right are for the Lynx, the suborbital space plane we're working on right now. The Mark I will be relatively low performance for a space plane. It'll only be able to reach Mach 2 and 200,000 feet. And it's kind of our practice bird for when we get some more technology together to do the Mark II, which will be able to hit 100 kilometers altitude, 330,000 feet plus, Mach 3.5. And I like to say it's going to be the hottest thing to take off from a runway ever. More acceleration than a fighter jet, higher top speed than an SR-71, and greater altitude than the X-15. And it'll be a plastic airplane that would fit in this venue right here, no problem. And all of us at XCOR are going to fly on that thing before any paying customers sit in the right seat. We like to joke about the difference between the chicken and the pig and a ham and egg breakfast. The chicken is involved, but the pig is committed. We're a bunch of pigs, I guess.
Makes you think twice when you want to design a part and be like, it's good enough.
Yeah, it changes your focus when you know you're going to be riding on it. Yeah. Well, let's go next. So what happens after we get to orbit routinely? Within 10 years, XCOR really plans to have routine daily access to orbit with a multi-seat manned vehicle taking people to and from space facilities like those built by Bigelow. Well, what happens at that point? There's a lot more things you can do up there. There's a lot more things that have to be done up there. And most of them aren't going to involve rockets. There'll be rockets attached to whatever's doing it, but the main propulsion won't be rockets, and that's what I find really fascinating. And tethers have tremendous possibilities. You can have just a plain old tether that dangles. You can have a tether that's electrically conductive, and that's what's illustrated here. That's called a terminator tether, and that's just basically an aluminum tape with a weight on the end of it that you can deploy from a satellite, and it cuts through the Earth's magnetic field lines, creates drag, and in a matter of a couple of weeks, that satellite will enter the Earth's atmosphere. And that's becoming increasingly important when you look at space debris. We'll get to that later. There's also, you can tumble a tether end over end so that you can grab things and fling them. You can tumble them in different planes so that you can use that electrodynamic stuff. You run a current through the wire, and it's the opposite of a generator. It's more like a motor, and so you're pushing current through it, and that's creating force against the Earth's magnetic field and accelerating the tether so that you can put something into relatively low Earth orbit, put up a tether and run current through it with solar cells, and the thing slowly climbs up out of Earth's gravity well using the Earth's magnetic field as a handle to grab onto. That's a pretty neat trick. And there's lots of things you can do with that. There's beamed power. Instead of having to carry all your energy on the vehicle in the form of chemical energy or solar cells, which are heavy for the amount of power that they put out, you know, you can get a little bit of power from solar cells, but you can't run a huge high thrust rocket engine off of solar cells. There's just not enough power there. If you beam power to it with a laser elsewhere, all the mass of the power plant is decoupled from the vehicle that's moving around. You can do exciting things with that. You can do solar sails where you have a huge, thin, gossamer object that intercepts sunlight, and that drags it around the sky. And you can combine various things. You can add beamed power to rockets. You can add beamed power to sails. And there's all sorts of combinations of these technologies that can become interesting in the future. And then last but not least, there's guns and catapults, but there's a couple guys here in the audience that know a heck of a lot more about it than I do. And I probably won't even get to that point. So next slide. The simplest tethers are just two weights and a string in between them. And the interesting thing is when you have something suspended on a tether, there's a real simple rule of thumb that if you're a certain distance from the center of mass, if you have, you know, a heavy object and a light one over there on a string, and it's just hanging vertically and you release it, the orbit changes because you're being held up. You know, consider you're in orbit and you have something dangling down below you on a cord. And if it's dangling like 1 kilometer below you, and then you release it, it's going into, because it's not going quite fast enough, because it's down below, even though it's going at the same angular rate around the Earth, it's going to drop down into a lower orbit from the space station that you're dangling it from. And it turns out the rule of thumb is about 7 to 1. So if you dangle it 1 kilometer and then cut the cord, the low point of its new orbit will be 7 kilometers below you. Now the interesting thing is, if you're in a space station at 400 kilometers altitude, and you reel something out about 50 kilometers on a cord, and then release it, its low point of its orbit is now 350 kilometers lower. The low point of the orbit is at 50 kilometers. It's going to re-enter. You didn't have to pay any rocket fuel to get this payload away from the station and send it back to Earth to burn up in the atmosphere or to re-enter. So the trick is you take like a Progress, which is a cargo vehicle sent up by the Russians to the space station, and it doesn't have a re-entry shield. When it leaves the station, they pack all the trash they've got on board that they can't reuse in any way. They pack all that on board the Progress, they undock it, and then it re-enters and goes shooting across the sky. And because it's coming in tangentially, it's a long, slow meteor, and it takes it a long time to burn up. So if you ever actually see a really slow-moving, spectacular meteor that, you know, keeps shedding particles and breaking up into a clump of stuff, that's a good chance that it's a re-entering Progress if you're out over the ocean, because they deliberately re-enter them over the ocean. But the thing is, you know, you see this glorious shooting star, and there's probably a lot of astronaut crap on board that thing.
Yeah, that is progress.
And they actually cost them more to deorbit that stuff because they have to have fuel remaining on the Progress for it to fly away from the space station and then do the deorbit burn to slow down a little bit so that it can finally dip down and enter the atmosphere. Whereas if when the Progress goes up there, you reel it out on a string, it's a conservation of momentum thing too. If you reel a ton out 50 kilometers, and you weigh like 100 tons, like the space station, it's about a 100 to 1 ratio. Maybe it's only a 50 to 1 ratio. The exact numbers don't matter. So if you have, say, a 50 to 1 ratio between the space station and the Progress that it's reeling out, and you reel it out 50 kilometers, well, that means that the space station is now about 1 kilometer above the original center of mass. So it's dangling up 1 kilometer from where it used to be. And then when you release that tether, the space station is now going to be in an orbit that peaks out 7 kilometers higher than it was, and you didn't pay a thing in fuel to do that. So
where's the energy go?
Say again?
Where does the energy come from?
Let me turn the gain back on here.
No, where does the energy come from? I'm just curious.
That what you're doing is you're kind of partitioning the energy. It's like in a roller derby. There's two gals skating along, and one comes shooting along, and she grabs the other and flings her. And the one that slows down is imparting momentum to the one that speeds up. And the total energy of the system hasn't changed much. So what's another way to
You're
put it?
robbing Peter to pay Paul. The
Yeah,
smaller
yeah.
one loses energy that the other one gains. If
Basically-
you look in the center of mass reference frame,
The center of mass always stays in the same circular orbit.
Yeah.
right,
Another way to ask that question would be, what keeps this cable, what provides the tension on the line?
That's a good question to do it. It's basically like a tide thing, is that the Earth's gravity falls off 1 over r squared with distance. So the higher you go, the lower the gravity. So that the lower you go, the stronger it is. So if you're in orbit, something a little bit above you, there's less gravity. Something below you, there's a little more. And so if they are both forced to go around the Earth at the same rate by a string tied between them, this one's getting dragged along faster than it wants to go, and this one's getting held up, going a little bit slower than it would prefer to go. So that's where the tension comes from. So that if you had a liquid blob in Earth orbit, it would stretch out vertically because of the tidal forces. It's the same thing. The moon's tides, the gradient in the moon's gravity field is what causes Earth's tides. And so the oceans try to get that same pointed at the moon shape, and that's the same thing that makes a tether work.
Does it require additional initial energy to get that mass that you're deploying downwards into the higher orbit? So you're essentially...
Well, is that after it's arrived at the space station, you unhook the two and you start reeling out the tether, and you need to do a little bit of springs or something to push it away from you and get it to start separating. But once you have a little bit of tension on the cable, the one that you're reeling out downward is kind of by conservation of momentum, just like a spinning skater when they pull their arms in, it's trying to go faster. So the weight that you're dangling down lower is trying to pull out in front of you, and that puts some tension on the line. And actually, you got to put a brake on the line to absorb some of that energy. And what it is that there's the tidal force is trying to stretch things apart. And so if you let it stretch that, it's like letting something run downhill. You're dissipating energy to do that. So it's actually that because the tides are stronger than the self-gravity of an object in Earth orbit is another way to do it. You're inside the Roche limit. And boy, that'll open up a whole nother can of worms. I'm not going to try to describe that tonight.
it's hard to talk about accelerating reference frames compared to the ones we're used to on Earth.
Yeah, it's like, you know, we could probably do some really, if we had a merry-go-round, we could do some really cool physics demos that would make it a lot easier to understand how tethers work. But
Live, take an action item.
and, well,
I don't have my notebook, I don't have my engineer's notebook, I can't take an action item.
and
We've got audio.
plus Dramamine, of
You're
course.
also suggesting that this is a means to bring the orbit of the space station up.
Right, so what you do is when you lower the trash to go burn up in the Earth's atmosphere, you're taking some of that momentum and putting it back into the space station. And the other neat thing is that while that Progress is docked with the station, you can unload all the fuel it has on board, nasty, corrosive, toxic stuff though it may be. You can scavenge all the fuel off of it for use on the space station because you don't have to reserve any for the Progress to fly itself away. You dangle it at the end of that line, you let it off at the right moment, it's going to burn up over the Pacific.
Are there any issues with releasing the lower orbit object because suddenly the total mass of the system might drop instantly by, you know, a
Well,
ton?
it's that, you know, from the point of view of the space station, you have this tether reaching downward to this Progress that's hanging down there, and there's maybe 100 pounds of tension on that line. It's not very much.
So just be a little bump.
And so, you know, you let it loose and you hear this twang. And while the Progress is attached to the space station, there's a little gentle acceleration upward. So, you know, if you're hanging onto the wall in the space station and you let go, then you'll slowly drift upward relative to the wall in the space station because there's just a little bit of acceleration. And down in the Progress, it might have, you know, like 1/100 of a g. So something would take, you know, 10 times as long to fall as it would at normal gravity.
How would you recircularize the orbit, since that is essentially one constant burn that?
Well,
is
so you know,
effectively
this
one
is
burn?
giving you a slightly elliptical orbit. It's
Right.
going from 400 to 407. And so the next time you drop a progress, it's a couple months later, and with any luck, you know, the timing works out so you can do that when you're at the high point of that orbit so that you raise the perigee. But in the meantime, you've also got drag, and you got to run your rocket engines occasionally to do drag makeup. So you just do the drag makeup for the 400 by 407 orbit. So it's not a big deal in that regard.
And the most important question for the purpose of our discussion, do you need any materials that you don't have today?
That line can be basically a braided cord. And people have flown similar tethers already in the past. The guy that you wanted to get here on a panel, Joe Carroll, at I think Tethers Unlimited or Tether Applications, I can never remember the names of the two companies. Tether Applications. He's built and flown several tethers in space, and they worked very, very well. And they were made out of really quite mundane materials. Just a braided spectra cord. Nothing spectacular.
Now, to
So,
do justice to this man's questions, if you
I'm sorry, I want to kind of.
Keep the interruptions to a minimum, yeah.
Because we are definitely going to have a lot of time at the end to really have a good discussion.
will say that.
Yeah, I don't have a lot of slides, and once I've galloped through them, I have a lot of source materials that I pulled the slides from, and if there's more interest in any one particular area, I can dive into the other guy's presentation and kind of translate for you. It's an impedance matching problem. And so the first use of tethers that you can use on a routine basis is just to deorbit stuff and raise the orbit of what you got it attached to. And then the other thing that's my own personal observation is that you can do that same short tether. It's only 45 or 50 kilometers long, dangling down from the space station. If you have a trapeze bar on the end of it, so that you launch something into orbit, and then instead of doing the second burn to circularize your orbit after you come up, you just grab onto that trapeze, and you're hanging there, and you transfer your payload to the elevator car that's come trundling down the cable, and then grab another payload that's going to return to Earth, and then you let go of the trapeze. And all that's done is it's kind of held you up while you were at less than full orbital velocity, and then when you let go, you're immediately back on a reentry trajectory so that you can have your reusable orbiter just let go of the trapeze, and then it reenters and lands. And it doesn't sound spectacular. It only saves you like 300 meters per second of velocity change. That's about 1,000 feet per second. But because the rocket equation is exponential, that 1,000 feet per second is at the far end of the almost 30,000 feet per second velocity change that you need to get to orbit. And that's some really expensive velocity change. So it turns out that just grabbing that trapeze so that you don't have to burn the extra fuel allows you to almost double the payload you can carry to orbit. And that's a spectacular win for a relatively small investment. And one of these days I gotta, find some people that are willing to do some experiments on that, but I'm too damn busy building rockets. So that's the thing. The trapeze catch, no circularization, no deorbit, and of course you can scavenge all of your fuel before you deorbit because you don't need to carry any more extra reserve fuel for the emergency maneuvering that you no longer have to do. Next. The real problem, before we can do a lot of really cool stuff out in space, is that there's too damn much junk whizzing around up there. This is a kind of an involved plot here. Let me pull a laser pointer out here so I can point at stuff a little better.
Is this your purple one?
Yeah, this is, it doesn't have as much contrast. I'm sorry about that. Total objects is that they can track with the radar. That's, this is things that are big enough to be seen with radar, and there's a lot more smaller ones that are too small. Is that down to about 4 inches, I think they can track, but smaller than that. Something 1 inch across hitting you at 10 kilometers per second will fuck up your whole day.
Is that technical English?
It's technical English for people that have to really deal with it, okay?
Indeed.
And there's lots of spacecraft out there. It looks like on this chart, over 3,000 spacecraft. There's close to 2,000 rocket bodies, close to 2,000 mission-related debris, which is like, adapter panels that pop off when something gets when it separates the payload from the launch vehicle. So there's thousands of roughly, car to bus sized objects up there, where if you get a major collision, you get a whole bunch of additional particles made. And here's a really good point to see here. That jump from there to there, that was China's anti-satellite test back in 2007. And that jump there was 2 satellites, one of them under control in Iridium, another one that had been abandoned in place years and years before. It had just been left in orbit after it died. That was a satellite-to-satellite collision that created another roughly 2,000 pieces of junk. And the trouble is that, you can have a car-sized thing that gets hit by something the size of a wheel, and you get hundreds of more wheel-sized things. And then one of those wheel-sized things hitting another wheel-sized object can make hundreds of smaller fragments, hubcap-sized thing. So that's where you end up, there's a worry that we'll get to the point where there's a cascade, where you end up with just so much crud hitting into one another, we end up with belts like Saturn, with rings. And if they're in all orbital planes, that pretty much makes low Earth orbit unusable, because there would be so much flying debris up there. It'd be like being on a battlefield, and you're not worried about the bullet that has your name on it. It's the one that says, "To whom it may concern." So, there's going to be a lot of these "to whom it may concerns" out there if we continue to allow this to happen. So the trouble is, you got to get all the big objects, which is where all this stuff comes from, you got to get rid of them. Next slide. And the guy that I wish could have been here, Joe Carroll, has been working on this concept, EDI, electrodynamic debris eliminator, and it's a fantastically brilliant idea. This whole thing, you see, it's 1 kilometer between collector solar array sets, and the whole thing is maybe 4 kilometers long, and it weighs about as much as I do. Most of its weight is just the tether and the 5 lumps on the thing. And this thing spins slowly, like every 15 minutes or so it's rotating. And it doesn't have to rotate in the plane of the orbit. If it's going around the Earth like this and it's tumbling along the orbit, that's the way you might expect to use a tether. But this thing can actually be rotating at a different angle. So it's doing this as it orbits around the Earth. And that allows it to cut through the Earth's magnetic field in all sorts of interesting angles so that you can control its orbit completely. You can raise and lower the orbit, you can change the orbit plane, and you can change the orbit plane relative to the Earth's poles, or you can change the orbit plane relative to the stars. There's 6 different parameters for an orbit. It's hard to describe how orbits work without going into some really god-awful math, so I find that gestures help a lot. You cut my hands off, I can't give a talk.
We've got a great picture of you with your smearing bird wings spinning around.
Oh, good, thank you. I just really needed that. So this tether, relatively small, relatively lightweight, you can launch 10 or 12 of them on one, you can launch 1 or 2 at a time as additional payloads on other launches, where they got a little bit of margin, they can just carry it on the adapter between the rocket and the payload. And it deploys itself, spins itself up by running currents through the tether in various directions. And so it can be putting current one way on one tether and the other way on the other, and that forces it to spin because one side is dragging relative to the Earth's magnetic field, the other is accelerating, and that makes it spin. You can make it spin in any arbitrary direction. You can make the whole thing accelerate in any arbitrary direction. And this thing can wander anywhere in Earth orbit between low altitude, where you're starting to run into atmosphere problems, and up to maybe 2,000 kilometers up. That's where all the junk is. So a couple of times a year, this thing can come close enough to another satellite in orbit, and the tips are only rotating at a few feet per second, because it takes 15 minutes for this 4 kilometers. So you're covering 12 kilometers in 15 minutes. So it's 40 kilometers per hour is the speed at the tip. It's nothing. And you just work that into all the calculations. Controlling this thing is an incredible nightmare because it's got so many degrees of freedom, because it's flipping, it's flailing, it's spinning, it's got 6 orbit parameters you got to monkey with. That's what number crunching is for, okay? You know, I've probably got enough number crunching power right here to do the problems. It just requires some people to figure out the math to tell the computer what to do. And once you can do that, each of these vehicles can grab one of those spent rocket stages, something the size of a car or a bus, grab it and return it to a central facility, and that central facility is in orbit, in some randomly chosen orbit, and you can actually station one of these near that to do additional boosting to keep that repository in place. Now what you do is you take this problem of thousands of satellite bodies in thousands of different orbits all over the freaking place, and it's hard to calculate when one of those is going to be a hazard to your satellite. You get them all into one place. You know, so if you keep all your eggs in one basket and then watch that basket really well, you've actually improved things. And once you've got all these things gathered together, this is the first asteroid mining we're going to do. They're artificial asteroids that we put up, and they're a hell of a lot better than anything that's, you know, 3 million miles away, and all it is rock. This is aluminum and steel and copper, and, you know, so there's all things that are already reduced metals that are going to be useful in a hurry, in a much earlier fashion.
How are you attaching it? How are you picking these parts up? I just don't understand how you're going to move it with this rope.
Oh, the tether can run current through its cord, and that pushes it faster. That makes its orbit climb. It can just passively let current flow down through it.
How do you grab the debris?
That's what this over here, the net manager, I'm sorry, I didn't hear the question clearly. Let me turn the gain back on. The net manager has a couple of hundred nets. Each one of them is, you know, about the size of a house and weighs maybe 50 or 100 grams. It's tiny. It's gossamer because the forces it has to contain are tiny, because it's not accelerating ferociously. It just has to basically lasso this piece of junk and hold on to it. And then it holds on to it while it's accelerating at some tiny, tiny fraction of gravity to manipulate its orbit to the point where it can deliver it to a facility where it just releases the net. You know, it releases the object, net and all, and something else grabs it and takes it to the store yard, the junk yard, the salvage yard. The other way you can do it is if you don't have that salvage yard, you just carry it down to like 300 kilometers altitude, and then in the next few weeks, the tenuous upper atmosphere, the last bit of drag in the atmosphere, will take care of the job for you. It'll re-enter and burn up. But you don't have as much control over it in that case, and it might re-enter and burn up over some civilized place and drop, you know, heavy things like pressure bottles on people's heads, and you really don't want to do that. And besides, it took so much energy to put all that stuff up there, it really seems like a shame to throw it away to burn up in the atmosphere, because it costs, you know, at current rates, thousands of dollars per pound to put something up. It really seems a shame to destroy that. So our next slide, I think. Oh, let's go back up. It looked like there was a lot of interest in this. I've got a presentation elsewhere on the drive that I can go through some of their slides that show this in more detail if you want to get into that later. That was one of the things I wanted to do with this, is a lot like the Space Up, is that it's kind of an audience-driven thing. It's whatever you're interested in the most, I'll go off in that direction for you, because there's so much more stuff than I could possibly cram into a couple hours of talking. And I can't possibly put out enough PowerPoint to keep it engaging for a few hours.
So then, on that subject, how close is this to being produced, and is it possible to get backing from some of the people, organizations who put that junk up there in the first place?
That's exactly what they're doing. The guys doing Eddie deserve to get richer than Croesus, because they're going to be doing...
We hope to get those guys in here.
To do a presentation.
So, we're going to go...
I will definitely be in the audience that time.
Yeah. So I'm going to go and recommend that we can keep on moving.
Okay, let's keep moving. Next slide.
You'll definitely get a chance to talk to those guys.
Now, once you've gotten rid of the big chunks of trash in orbit, there's still all the smaller things. And this is a way to address the smaller objects. This won't be able to deorbit big stuff. And the smaller things don't weigh all that much, so just getting them to the point where they will enter the Earth's atmosphere and burn up is solving the problem, because they aren't a valuable resource in and of themselves. They're just a hell of a nuisance. It's like having starlings around. So the simplest way to do it is you just have a big laser on the ground with a big fancy mirror with adaptive optics to take the twinkle out of the beam as it goes out. And I'm glad that wasn't me, because I don't think I turned my phone off either.
Let that be a reminder to everybody.
Here, and you can turn mine off. So it's embarrassing when the speaker interrupts himself with his own cell phone. So the trick here is just you use basically a weapons-grade laser, which is the biggest political problem with this.
You think?
You get this on eBay.
Well, the thing is, the people whose lasers whose satellites might potentially be attacked with lasers, they have nukes. Okay? The reason there hasn't been a major war since World War II is that everybody's gone, oh shit, that's too scary. Mutual assured destruction works. Okay? The only people that have fought major wars have been folks that haven't had nukes on both sides. You might notice that. So anyway, off the political and back onto the practical here. You just give a zap with the laser and it vaporizes a little bit of the target object. And because you're zapping it as it comes toward you, that exploding pulse of gas is exploding back toward the laser, which means it's slowing the thing down. You're basically tapping on this thing by remote control. And what you do is you don't even bother to track individual objects all that much. It's just your system mostly looks to the west because most things are coming from the west, although you do have to look north and south for the ones in polar orbit. You don't have to look east. The only stuff coming from the east are like 3 satellites that got launched by the Israelis over the last 10 years. And they don't dare launch anything to the east because that'll start a war. So they launch from on the coast in the Mediterranean and they thread it through the Straits of Gibraltar. And so they've got stuff in it. It's always on a 143-degree inclination orbit. If you go through the orbit tables and look them up, it's like, okay, there's these weird ones in this totally peculiar orbit. It's because that's the only azimuth they can launch to without somebody shooting back. So, okay, I suppose that eventually if there's some junk to be worried about from Israel, you can turn the laser around. But mostly it's looking east. Mostly it's looking west, a little bit north and south, and it's just tapping on everything that comes by. And over the course of a couple years, one facility can clean out all the crud that's at its orbital, its latitude or less. See, if you have something in an equatorial orbit and your laser is at 30 degrees north, it's never going to see the stuff in equatorial orbit. Thankfully, there's not a lot of low Earth orbit crud in extremely low inclination orbits. They're all at 28.5 degrees or more, which is basically, where Cape Canaveral is. A lot of us are in 51-degree orbits because that's where one of the major Russian launch sites is. So between the eddy and the lasers, you can get rid of the trash in orbit. And then you can really start having fun with everything else, because then you can start using more tethers for more things because you don't have to worry about the tether getting cut by orbital debris. So basically, you got to pick up the trash before you can go out and play on the playground. So next slide.
Before we go on, I personally would like to know, what cases have there been beyond the Cosmos collision of orbital debris interfering with the operation of a space mission?
Well, occasionally the space station crew has to hunker down in their Soyuz vehicles, ready to batten the hatches down in case the ISS gets hit by something, because they can track things, but the last couple of miles worth of cross range in tracking 2 objects going at high speed, and you never know exactly where both of them are, is really quite difficult. Now with the Yeti that's trying to grab things in orbit, it has the advantage of sneaking up on the target slowly, so it can look at it and see it from close up, and basically use a camera to look at it in sunlight and see where it is relative to the stars, and that lets them do the navigation more precisely. But when you have two things that are on the opposite sides of the planet at one point, and half an hour later they're in danger of collision, then it's really hard to predict exactly where both of them are going to be precisely enough to know whether or not they're actually going to miss, which is why they have to hunker down sometimes on the space station. And other satellites end up using up some of their rocket fuel that they have to ration out in a very miserly fashion, because it looks like, looks like next Tuesday you'll come within a mile of this other satellite. So one of the two has to maneuver to avoid the other one, and they burn up fuel in the process. So it's not been a lot of collisions. That one was enough to wake everybody up. But the trouble is that it's shortening the life of every satellite. It's incurring extra costs. So if you get rid of all this stuff, you reduce the problem dramatically, because most of the encounters are with junk rather than with other active satellites. And the collision was between an active satellite and a dead one that was no longer under control. So, beamed power is kind of a natural offshoot from the laser trash collection. And a friend of mine, Jordan Kerr, has worked quite a bit on beamed power systems where you have basically just a flat panel on the side of the rocket, and it's a heat exchanger. You just have tubes running through it with your rocket fuel, which can be something like hydrogen or nitrogen or ammonia, and you run that through the heat exchanger. A powerful laser beam illuminates the vehicle, and this drawing is not all that accurate. This beam is a hell of a lot wider than the rocket vehicle is. It might be 5 times wider than the rocket, and only 4% of the beam power is actually being intercepted and used. But that's okay. If the beam power is cheap enough, who cares? Now you want to make sure that there's nothing behind this guy. They might go, whoa! But the trick is that you can have a very simple, lightweight vehicle. It's just pressure fed. You can have something like ammonia, which when you heat it up hot enough, it breaks down into nitrogen and hydrogen. And it actually gets a pretty good exhaust velocity for a fairly dense propellant. And so this lets you do simple, lightweight vehicles which can do quite a bit of velocity change at relatively low cost after you've paid for the laser. So this would be something that you would fly 20 of these every day, just hitting them with the laser and blasting them into the sky. So next. And beamed power can also be used with solar sails. That if you've got a solar sail that works on sunlight, which is pretty thin gruel for a solar sail, it takes a long time to get anywhere. But you can actually get acceleration greater than 1G with enough concentrated light power, either lasers or microwaves, or basically anything else that you can make a coherent emitter that you can focus really tightly over a long distance can be used for beamed propulsion. And science fiction writer Jim Benford is also a physicist, and he was working on some graphite solar sails. And the thing is, it's not tremendously reflective. It doesn't reflect the beam too effectively, but it can take tremendously high temperatures, because if you focus megawatts onto a teeny tiny area, and you only absorb 1/10 of 1% of it, you still have to dissipate kilowatts. So it turns out that their solar sails end up glowing because they're at thousands of degrees just from the power that they haven't reflected. And the neat thing is that you can get high acceleration. If you have microwaves, you can have something that just has tiny thin wires that you can barely see with the human eye scattered at roughly half the wavelength of the microwave. So if you have microwaves with a wavelength like that, you can have a gossamer thin wire every inch or so. And that weighs approximately nothing. They're talking about a device, a wisp, 100 meters across, 300 feet across, bigger than a football field, that weighs maybe a kilogram. So it would have almost no mass to it. You hit that with a few billion watts of power, and that sucker starts off at many, many G's acceleration. And you could launch something toward the nearer stars that would get there within a normal human lifetime without having to have generation ships to get it there. Then as it's falling through the target solar system, you zap it with another beam. Actually, years before it gets there, you send a burst of microwaves after it, and which spread out to a much larger area. So you don't have to know exactly where it went. If you get the beam big enough on the sky, you know you're going to hit it somewhere out there. And it gets enough microwave power there that it has, you know, little integrated circuit chips, and you know, if you have something the size of a smartphone with its cameras and such on board on a 1 kilogram vehicle, it can do a lot of science while passing through another solar system at 10% of the speed of light. And so this is all stuff that's actually physically doable. They've demonstrated lifting solar sails against Earth's gravity just by concentrated microwave and laser power. And it's just an engineering problem. It's not a physics problem. You can throw enough money and engineering time at it, and you can actually make it work. And it's a lot of work to get it to the point where it's reliable. But when you get there, you can do some really cool stuff. And that's what I'm trying to concentrate on today, and not the science fiction warp drive crap that nobody really knows how to do it. This could actually be done. And the next cool thing.
I'm sorry, I just had a question. The sails would be made out of what exactly? Like carbon nanotube fiber or something?
The high power sails that are getting zapped with a lot of power have to be made out of something which can take high temperature. If you have something that's just bouncing sunlight, it can be aluminum that's maybe 100 nanometers thick. And you know, it's less than a wavelength of light thick, and it also has holes in it because it only has to reflect most of the sunlight. So if you held up a piece of this stuff, you could see vaguely bluish light through it because the shorter wavelength light would actually be able to pass through. So that's how gossamer it would be. And if you handle a piece of this stuff roughly, it just turns into a gray smudge on your fingers. It's just amazing how lightweight it is, because they're talking about, less than a gram, a few milligrams per square meter. And you can go through, I don't have the time to go through the calculations, but somebody who's got a calculator can figure out, okay, if it's 100 nanometers thick and has only 5% solidity, then what's the mass of aluminum per square meter? And I think John will have numbers for us in a little bit here. It's easy to be able to farm that out.
Here's a question in regard to that. Does there exist in metallurgy base, like, you know, is that an impossible object to build?
One of the coolest ideas for solar sails is to make it more of a fractal structure, where you've got this thin film, and then every 10 centimeters or so, you've got a thicker bit of film. And it's all done by metal vapor deposition. And then every 100 centimeters, you've got an even thicker bit of film that's been projected. And then about every 10 meters or so, you've actually got a wire which has been bonded onto it. So it's got multiple layers, and then it's also 3D built up so that you've got kind of a truss structure out in front of it that's mostly transparent.
It's like a branching plant.
Yeah. So it's basically like a tree that's been genetically modified to have a solid canopy overhead, and conceive of that as the sail itself. Yes. And then all the twigs and the larger branches and the larger branches, and then finally the tree trunk is the structure to it. And it's all gossamer and incredibly lightweight, and you just have to manufacture it in an automated fashion.
And the number you're looking for is about 14 milligrams per square meter for just the final layer of canopy, so maybe 20 milligrams per square meter for the whole structure.
So that's like, how much per square kilometer then? Multiply that by 1 million?
14 kilograms per square kilometer. Yeah.
14
milligram times 1,000.
Yeah. So that, you know, an entire square kilometer, you know, I could carry in one hand. Okay? Yeah, so that's the only, and that would actually be able to get useful acceleration just by bouncing sunlight.
Handle with extreme caution.
Well, it has to be built in space. But you know, so you take some of the aluminum from those spent rocket upper stages and feed that into a foundry that uses sunlight to vaporize the aluminum, and then just project it onto a surface where the aluminum condenses out. And then the trick is to peel the aluminum off of there, so it has to be basically a Teflon surface. so that it's not bonded on there tight. Or you can make the surface is made out of something you can evaporate and recapture. So there's a whole lot of games you can play with that.
Do plastic and then turn around and let the UV deteriorate the plastic. You're done.
Well, you don't want to put 100 times the mass into the throwaway part as you do into the solar sail. You know, you want to be conservative on this stuff. But anyhow, you can build things in space once you've got routine access up there, once you've got stuff up there all the time, and you don't have all the crap flying around in orbit to screw up your solar sail plan. But even before you get to the solar sails, it turns out you can get from lunar Earth orbit, from low Earth orbit, to the surface of the moon and back again at a total velocity change increment about like getting onto the highway. Because you can do it with almost no fuel by using tethers to actually grab you and fling you on the translunar trajectory. Another one at the moon grabs you again and sets you down on the surface, or just 50 feet above the surface if you're paranoid about the accuracy.
What kind of time frame?
Yeah. It's like any other flight to the moon.
3 days.
3 days.
Good.
Now, if you that would have only occasional access because it's the way the orbits precess and so on. You got to make sure that the lunar tether is in the right orbit plane at the time that you arrive at the moon. If you have other constraints, the worst case is that for a cargo launch, you send it off toward the moon and it does a flyby of the moon to change the plane of the orbit it's in, and then the next time it comes around, it ends up getting grabbed and set on the surface. But you could do a manned flight from Earth orbit, so you're sitting there and essentially like a Dragon capsule would be a good example, with a mast sticking out the nose of it maybe 50 feet with a couple of sideways barbs on it that the grapple mechanism can grab. And you're sitting there going whoop-de-doop-de-doo in 0 G, and all of a sudden this thing comes swooping down, grabs you, and all of a sudden you're at 3 Gs and it flings you. Over the course of about 15 minutes, you're at 3 Gs until you get to the right velocity and it releases you. And at that point, you're on your way to the moon.
That seems very difficult.
It's actually, particularly if the target is cooperative. So well, no. It's the military tries to figure out how to get two objects to come together without any cooperation. And this is like an aircraft hitting a tanker, because the velocities at the moment of encounter have gone to 0. Now, the accelerations are significant. From the point of view of the spacecraft sitting there in orbit, you look up and you see the end of the tether coming down at you, and it's rushing towards you. 10 seconds before grapple, it's coming towards you with the speed of sound. It's closing on you at 300 meters per second, but it's decelerating at 30 meters per second squared. So in those 10 seconds, it comes to a halt, and it has a sub-tether on the end of it that can reel out, and probably has some thrusters on it too, so it can maneuver sideways a little bit, so that as it's coming down, you've got radar and cameras looking at each other and measuring all the velocities and positions as you're coming together, so it can just grab it as it comes by. And might have seen some idiot entertainment thing where a guy was doing a bungee jump, and he bungee jumps from a tower, comes down, and he's right over a padded mat. And they did it with dummies first, and then with him coming to a halt 10 feet above the mat, and then they lowered the cab a little bit, so he came down a little bit closer. And the guy came down, and just as he came to a halt, cut away and walked away from it. Okay? If you can do that with the Mark I human eyeball, you can do it with computers and cameras and all the radars and lidars you want. So he was doing the same sort of problem, where he's approaching the target quickly, decelerating and coming to a halt just at the right point. And his releasing from the bungee cord was the equivalent of the capture. And so it's physically doable, and it's not that big an engineering problem. It's scary as hell to contemplate, but it's doable.
How long of a tether would you need to get what's, I guess, about a 3.5 kilometer per second delta V effective to get from LEO to escape velocity?
Yeah, so we'll go to the next slide. And so we have a tether that's initially in an elliptical orbit. And I think this is to scale. That's the length of the tether. So this tether is only like 200 kilometers long. It's not trying to stretch all the way from the equator out to geosynchronous orbit and beyond like a space elevator. This is a much more reasonably sized thing. And it's made out of a fairly strong material like spectra. It's not made out of unobtainium. It doesn't have required, carbon nanotubes and fairy dust to make it work. The thing is tumbling along, and it comes along, grabs the payload, and flings it out. And when it does that fling, the perigee doesn't change, but the apogee over here gets reduced because it's lost some momentum. And if people are more interested in this, I can pull up later the article that I pulled this from, and that has more information such as what the mass ratio is. I think it's only like 20 to 1. The tether weighs about 20 times the object that it can fling. So if it can fling a 10-ton object, it only has to be a 200-ton tether. And at the prices we're looking at putting things up in the next few years, that could actually be doable.
And most of that is just lead.
No, actually most of it is just the tether. And it's got a counterweight at the other end, but most of the mass is the tether itself.
So the mass is distributed, it's a cable.
The mass is distributed along the length of the cable, and you get your best momentum store just by putting all that mass into cable rather than a counterweight.
So does it need to recapture something coming back from a lunar orbit?
It can do the same thing, and that will pump its orbit up again as it deposits it back in low Earth orbit. This is inherently a two-way system. It's not like a rocket where once you burned your fuel, you're on a trajectory to the moon. Well, now what do you do?
So actually, if it's got materials from the moon, if they're mining or something, it'll actually put into an even higher orbit than its initial. It'll have more mass coming back.
There's several ways. The tether has lost orbit, lost energy by doing the fling. Now you can, each time it gets down to a low enough altitude where it can interact with Earth's magnetic field efficiently, where there's enough ionosphere to be conductive enough, you can grab some electrons. It can do the electrodynamic tether bit, and it can pump more energy into its orbit electrodynamically, just like the other guys, so that it can regain the energy. And the neat thing is that all these systems don't use up propellant. Instead, you're using solar power to run your space transportation system, which is really quite a slick trick.
Before we get too deep into this concept, are there more concepts that you have on the plate for tonight?
Yeah, let's keep moving here.
Let's go ahead and keep moving. And if anybody wants to ask more specific questions, put a pin in it and ask him when we're done overviewing everything.
I've got more stuff for that, yeah. And so when you get to the moon, the rotavator, the lunavator at the moon is initially in a slightly elliptical orbit, but not tremendously so. And you can see here the scale of the tether relative to its orbit, and basically it has to reach from its orbit down to the surface of the moon. And after it grabs an incoming payload and puts it down on the moon, it's gained energy, so its orbit goes up. Simple enough. And of course, because this is an entirely almost lossless system, that tether can come spinning around, a day or so later on the next it only takes it like 2 hours for this orbit. So ideally, 2 hours later, you could come back over the same site where you dropped something off earlier, and another vehicle can be waiting there. You grab it, take it around. You might have to do 1 or 2 revolutions before you're ready to fling it in exactly the right direction. But then you fling it off towards Earth. This lunavator's tether orbit comes right back down to where it belongs, and you have a vehicle full of probably lunar liquid oxygen, and if you're at the poles, maybe some methane or hydrogen for fuel. And so you take this vehicle back to low Earth orbit, where the other tether grabs it, delivers it to low Earth orbit, takes the energy out of it, puts it into the tether. And so what you're doing is you're sending expensive finished goods, all the computers and machines and motors and stuff that you want for the lunar base, and you're replacing them with cheap mass from the moon. So the net mass flow can be 0. If you're using the electrodynamic tether to boost it up, you can actually send more mass in one direction than the other. And of course, the lunavator, if it needs more momentum, you have to have some sort of rocket propulsion on that to keep it in orbit, because the moon doesn't have enough of a magnetic field to let you do the electrodynamic tether. So let's move on. Whoops, that was the last of the slides. I thought I had a lot more presentation, but I just ran out of time while preparing for this talk, folks.
So at this point, we're going to go ahead and open it up for people to ask about whatever they want to ask. Everyone would ask the rocket scientist.
Okay, there's a guy in the back here in black shirt.